Hello. 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 Now
Yes,
I'm
sir.
audible.
You are audible. Yes, sir.
Okay. Okay. Sorry. So okay. So today I don't want to take too much of time. I will just wrap up within maybe 30 minutes, maybe 50, 25 to 30 minutes, just to discuss two or three topics that will help to your for your next assignment. So they have assignment. That's right. So okay. Uh, I'm just sharing my screen. So okay. So the screen is visible, I guess.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Yes, sir.
Yes, sir.
Yes, sir.
Okay. So okay, so I think in the last class, I think Ames. So somebody, please, can you please all mute yourself because then there will be noise background noise. Okay, so the last class, Ames sir taught about the topological sort. Okay, uh, and the thing is that we can do topological sort in two ways. So we can do it DFS and we can do it BFS. So that is it. Okay. Now we can ask. So just for a refresher. So I will do the topological sort with DFS. So just take an example. Suppose this is the example. So this is a 5 and then 2, then 0, then 4, 1, 3, and 2. Okay. So with DFS, I will do that. So basically start with any vertex. So maybe you can start with 5 or 4, any vertex. So suppose we will start from 5. So what will we do? We like, so basically we start from 5. So we are calling maybe calling 2. So we are calling 2, and from 2 we are calling 3. So we are calling 3. From 3 we are calling 1, and from 1 there is no other options to other options to go. So we'll back from 1 and we'll push this 1 to a stack. Okay. Okay. So again from so we are here now, but from 3 there are no other options. So again we will back to 2 before backing. So we'll push 3 to the stack again. So we are now in 2. We are now in 2, but there are no other options to go. So we are back to 5. Before that, we will push 3 to the stack. Now from 5 we can go to 0. But from like from 0 there are no other options to. So we push like we back to 5 and push the 0 to the stack. Okay. So again, then again from 5 there are no other options to go. So we are back from 5 and push the 5 into the stack. So now just one option left, 4. But 4 from 4 all the like 0 and we can visit 0 and 1, but all 0 and 1 are already visited. So there are no other options. We back from 4 and push 4 here. So this is the stack. Now if we pop 1 by 1, that will be the topological stuff. So 4, 5, 0, 3, 1. So this is the topological. So
Sir,
okay.
sir,
Okay, there are too much noise.
sir, how is this 4 come into the stack?
Just can you please all mute? Just who are asking the unmute and ask. It's been very difficult. Like
Sir, how is this 4 come into the stack?
yeah. So so you why there is a background. So okay, so you already visited 5, 4, 2, 0, 3, 1. So you only have one option left. So you need to visit this. So what is the so how will you do the DFS for all the vertex in the graph? You will do the DFS. So 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 some like when you call for DFS 5, DFS 5 will call DFS 2, DFS 3. So all these things will be covered by 5. So only one vertex will be left, that will be 4. So 4 will be called. So DFS 4 will be called. But from DFS there are no way to go. So you are so are you getting my point?
What was the need to keep it at the top?
What?
Sir, I wanted to ask that what is the use of keeping it at the top? Because it's not even connected. How are we saying that it is at the top order?
Top means so what is the definition of topological? The definition of topological sort is like if in the graph there is a vertex u and there is a vertex v there is an edge between v to u. Then in the topological order u will appear first like before v. That is the thing. Now if you take this ordering, so you can see that this ordering will follow this property. So you can say like if look no it depends. Look, it depends upon from where you start the DF. So if you start the from 4, then this ordering will be different. Okay, but whatever the ordering is, it will always follow this property. Okay, so if you can check, like like uh, like take this example, and we will start DFS from 4. Okay, so what
Sir,
will be the
sir, in this,
order? Hello.
sir, in this question, if you start from 5, then like anyway we can't reach 4, no, sir.
Yeah. So but there, what is the point?
But then how is it like? Then how are we pushing into stack without reaching it?
So you know the algorithm. So algorithm is starting like this way. For all vertex v from belong to the graph, you need to do the DFS of v. So in that's it. So in the vertex, what is the vertex that 2 0 4 0 1 3 4 maybe. So this is in your graph Z. So when you start with the DFS 5, it will cover 5 2 0 1 3. Okay, but also when you are back, you are like getting back from 5, then only one option left. So you need to come here. So you need to check. So it is not like that. If you start from 5, you will just do this and you will leave this thing. So this is the algorithm. So for all the vertex you need to do. So this is the let's check. So it is like this. I'm just writing writing the same code. So for all vertex B, okay, check B is visited or not. Okay. If check if is visited. Okay. If yes, then you don't need to go. Else you will go DFS. So this is like so. So in the graph, 5 3 is I think 2 3 0 4 1 This is the graph. So how will this? So suppose you are starting from 5. So you are checking, okay, so if 5 is visited or not. Okay, it is not visited at the path. So you are starting from DFS 5. Then DFS 5 is calling DFS like this. So this is a recursion. So I am not writing this, but this is a recursion. When you are so like 2, 3 DFS 3, it will cover all this. So like this, just 4 will remain. So when you are getting this DFS call will, after that it will get back again here. So then you need to start from 4.
Sir,
Yeah.
but in the adjacency list, sir, there is no element which has 4 as its neighbor. So how we can
Yeah.
reach there?
You don't need that adjacency list, no. So we are looping by age, by nodes. So for all V or V in G, just so okay. So just write the adjacency list. So for 5 it will, for 0 it will 502. From 4 it is 0, comma 1. For 2 it is 3. For 3 it is 1. Okay, so that's all. So how will you go?
Sir, 0 is also there.
Okay, but 0 don't have any. Just write this. Then I need to write 1. So by this thing, so you need to check all the nodes. You need to check all the nodes. So suppose you are starting from 1. So what will be, so there is no way to go. Okay. So you are calling DFS 1, but you cannot go anywhere. So again you need to back. Again, you need to back to the main function. Okay. So before getting back, you are just pushing 1 to the step. Now okay, and you are also maintaining your visited array. Okay. So 1 is already. So this is visited. So now we are checking 0. Okay. Again, for 0 there is no option. So DFS 0 will return with nothing. So before returning, you just push. Now for 5. Now 5 will call 0. But 0 is already visited. So we don't we don't need to go to 0. So it will call. So just write DFS 5. 0 will not be called. So we'll got DFS 2. Okay. Okay. Again in the stack, DFS 2 is already visited. From DFS 2, we are calling DFS 3. We are right. From DFS 3, we are calling DFS 1. But 1 is already visited, so we are not calling this. So let's get back to 3 and push it in the stack. And check if from 2 there is no other way to push it. Again, get back to 5 and 2. Okay, so and now from 5, not from 5, there is no another way to go. So you just okay. I just forget to add 5 to the visit array, so it will be like so now. Okay, now it come to 4. Okay, now from 4, so DFS 4. Now from DFS 4, you can go to 0 and 1, but for both 0 and 1 are already visited. You are not going anywhere. So you need to get back to the main function. Right, for yeah. All 2 is already visited, 3 is already visited. So this is the stack. Now if you pop 4, 5, 2, 3, 0, 1. This is a topological stack. Are you getting my point?
Yes, sir. Understood.
Okay.
Sir,
Okay.
excuse me, sir. Sir, why is a stack necessary? Can we not just assign a allocate a array of size n and then fill up the array in the reverse order?
But how will track the function call?
Sir, I mean we can pass the array through the function and the pointer to the last element inserted, and then we can just fill up the array, so stack won't be necessary.
Still, maybe I'm getting your question. So
Sir, I mean we can just we know that the stack will contain uh, exactly the number of nodes we have in the graph. So
okay.
we can just make an array of uh, size of b, and
Okay.
then we can just pass that array, and initially we pass the last pointer of the array, so it's the address of a n minus 1, and then we decrement that pointer uh, as we add new nodes to the array. Will that be possible?
But what will be the ordering? So how will you maintain the order?
We
Like
can
I
also
anything
mean,
So
order.
what he's saying it is possible. What
yes,
he's
sir.
saying it is possible, sir. It can be done.
We shall fill.
Okay, so maybe actually I'm not understanding the question. If it is possible, then okay. Also, okay, you don't waste too much of time. Let's get to the next topic. Next topic means we can, I think aims are already discussed, but we can do it with DFS also. Okay. So take the same example. So 5. Now here the thing is that first you need to calculate what are the nodes with 0 degree. So you need to find all the nodes with 0 degree. Okay, and you just need to push not in queue. So this is the queue. So okay. So what is the degree of it? So it is in degree. Okay, 0 in degree. So the in degree of this is 0. 4 is also 0. It is 2. It is 1. It is 1. So okay. So first you just NQ 5 and
and you all have a result queue. This is a result. So so each iteration you just dequeue the front element from the queue. So you are dequeuing 5. So you are adding to the result list. And what will you do in the graph? You will decrease the integers of this neighbor. So for 5 there is 2 neighbor, 2 and 0. So you just decrease it in degree. So from 1 it is 0, from 2 it is 1. Again, because in degree of 2 is now 2. Yeah, now in degree of 2 is now 0. So you need to add like add 2 to this queue. Okay. Now next element is 5. You are just dequeuing and n2 into the result list, and you also check fourth neighbor and decrease their in degree. So fourth neighbor are 0 and 1. So we are just decreasing, and it's 2 1. So 0 is in degree becoming 0. So we need to into this again. You need to dequeue 2, add to the result, and check its neighbor. Check its neighbor is 3. So you need to decrease its integrity to 0. So its integrity is becoming 0. So you need to add to the queue. Now you dequeue 0 and add to the head. But from for 0 there is no neighbor. So you don't need to do anything. So now you are just dequeuing, add to the 3 here, and check where 3's neighbor is 1. So you decrease its integrity to 0 and add it to the queue. Again, last element is 1. There is no other way to add to the queue. Okay, so this queue is empty now. So this queue is empty. Now check the node count of the. So this is the result. So this is the topological sort. This is the topological sort. Now there is another condition you check. So for this question it is fine. But suppose in the graph there is some loop or cycle. Okay. So there are some cycle in the graph. You will see this result. So this result Q count, like element count, should be lesser than the actual graph node count. So then you can tell, okay, this graph is contain a cycle. Else you will find that topological. So is it okay?
Sir, can you again explain how you are filling the initial error 5420? We are first putting the 0 degrees 54. Then
Okay.
onwards.
Yeah. So yeah, you are just first we are inputting 5 and 4. Then decode 5, add to the result queue, and check 5's neighbor. So 5's neighbor are 2 and 0, and decrease their in degree. Okay. So previously the 2's in degree is 1 and 0's in degree is 2. So you just decrement by 1. So it became 0, it became 1. So as 2 in degree became 0, you need to add to your queue. Again, you need to follow the same cycle. Is it okay? Or?
Sir, here 3 and 1 are independently adding to the queue. Are they coming from their? They're coming directly. I mean, directly from their degree, not from any path Is it, sir?
No. Yeah, from degree, but like initially your queue contains the 0 degree element, and then you need to dequeue or dequeue the element, and you need to check breadth wise. Breadth wise, you need to check. So you need to check its neighbor, all the neighbors. So five neighbor, 2 and 0. So and you decrementing there in degree. So you are doing DFS. While doing DFS, you are doing some extra tasks. So you are decrementing there in degrees, adding to the queue. So basically, you are doing DFS only. You are doing
Yes, sir.
DFS only.
After 0, should we NQ 1 or 3?
Yes, sir. Means we should NQ 1, sir, because the neighbor of 4 is 0 and 1.
Okay, so then I maybe I have made some mistake, but algorithm is clear.
Yes, means like we have to NQ first the neighbors and continue decreasing their this degree in degree and then add them into the queue.
Yeah. So do you want to do like? Will I do it again? Like maybe then it will.
Yes, sir. It would be much helpful. If you did.
Okay. Just. Okay. So this is the graph. So okay. So just write the in degree above each of the nodes. 0, 0, 2, 1, 1. Now just this is our result queue, and this is our running or temporary queue. So what is the algorithm? At the first, you need to add the 0 degree element to the queue. So you are adding 5. And now your algorithm will start. So you dequeue 5, add to the result, and check its neighbor. So 5 neighbors are 2 and 0. So you are decreasing their in degree. Now while doing so, the in degrees of 2 is getting 0. So you need to add the now we are going to 4. Now you are going to 4. And fourth neighbor are okay. You need to add to the now fourth neighbor are 0 and 2. You need to decrease them. So while doing so, 0 in degrees become 0. So you need to add to. Again, you need to queue the top of the queue here. Add to the now 2's neighbor are 3 only 3 of those only 3 is the neighbor. So you just decrease that degree. Now as this becomes 0, you need to NQ it. Now, but from 0 there are no other options to go. So it's okay. So go. You are decreasing 3 and decrease its neighbor. So you are adding 1 to the queue. Now from you are decreasing 1 and it's done. So this is the so basically I think you are asking, so it is not like BFS for each element. So you are not liking doing this basically, so it's A, B, and C. So A's neighbors are B. So but here you are not like including B and C. So this is not like BFS, but you are following the queue technique. Queue technique, and each time when you are dequeuing an element, you are decreasing the integers of all its neighbors. So that's why it is comparable for like with BFS.
So, sir, in BFS, we don't add NQ until a degree is 0, even if it is the neighbor of the previous dequeued one.
Yeah, so no, that's what I'm saying. It is not like it is not equivalent to BFS. I'm just saying that, so it is a kind of BFS because like for like when you are checking for 5, you are decreasing all its neighbors in degree. So it is kind of BFS. So that's why that's it.
Excuse me, sir. Hello.
Hello.
Yes, sir. Yes, sir. After dequeuing the 4, we should go for the neighbors of the 4. So we should go for 0 and 1. We should enqueue the 0 and 1
Yeah,
after.
no, you are going for his neighbor, but you need to also check his in degree. No, if it is 0,
Yes,
then you need to NQ. Else you will not NQ. So that is the difference with BFS. So in the case of BFS, you are not checking integrities. You always NQ its neighbor. But here, before NQing, you need to check its index.
So, sir, if we consider only BFS, then we NQ 0 and 1 side by side. I mean, after 0, 1 will come.
Yeah. So yeah, if you do the if you do the BFS, like this is your graph, then what you will do? You will take 0, then you will NQ 0 and 1. So it's you all its neighbor. But here you just need to check is the in degree 0. If yes, then you need to NQ. Else you will not NQ. That is. And another important thing is there. What I'm asking, like in the previous slide. So you need all you can check the cycle in the graph. So if the number of nodes in the result queue is less than your vertex set, then your graph should have some cycle. So if someone giving some graph and ask, can you tell is the graph contains some cycle? You can use this in this example.
So, can you repeat the condition to find the cycle?
The cycle part?
Yes, sir.
Yeah. So I'm saying that after finishing the algorithm, if the number of elements in your result queue is less than the number of vertex, then the graph has a cycle.
Sir, but number of vertices and the elements in the result will always be same, right? Because we will visit every vertex.
No,
So
no, just see this example. Just see this example. That is what the corner case is in. Suppose this is just small. So you can see this graph has cycle.
yes, sir.
Yeah. Okay. So this is the extreme example. You can see why it is extreme. So in degrees 1, here is also in degrees 1. Here is also in degrees 1. So your algorithm will not start because like the first step is in the temporary queue. You need to add the nodes with in degree 0. But here you don't have any node with in degree 0. So your temporary queue is empty. So as temporary queue is empty, your result queue is also empty.
Yes, sir.
So the number of elements is result queue is 0. But in your graph there are total number of 3. So
Sir, if we take a node which has
what?
Sir, if we take a node with value 1 and direct it towards 5, then
So you are asking to add another node
yes,
here?
yes, sir.
Okay,
With
just
integrity 0.
helping. Okay, so just 0 is here. It's in degree 0. Okay, so this is the temporary queue. This is your result. So so you are adding 1 to your temporary queue as 0. It is in degree 0. So you are adding 1. And what will you do? So your algorithm will start. So now you will dequeue 1, add to your result, and decrease its neighbor in degree. So
Sir,
now
it has
5.
initially of 2, sir. Now it will become 1.
What?
The 5 has integrate 2 now, sir. Initial.
Oh, sorry. So it will get 1. Okay. So your temporary now your temporary queue is empty. Okay, but there are no other elements you can enqueue into your temporary. So your algorithm will terminate. So what will be the number of element your result queue? 1. But in the graph there are 4 elements. So there is cycle.
Okay.
So it is clear, no?
Yes, sir.
Yes, sir.
Okay. So I will not take maybe 2 to 3 minutes. Just to give some example. So what kind of applications of topological? So one of the applications is obviously the cycle detection. Okay. So I do emphasis on this because you already have seen the example. Another thing is then deadlock detection. Same thing as cycle, just the name is different. So what is deadlock? So suppose A and B have 2 resources. So suppose A is a person, B is also a person. So for A holding a pin P1 and B is holding another printer P2. Okay. But to complete A's task, he needs P2 and completes B's task, he needs P1. But both are waiting from one another. So thinking, okay, so I have P1. So when B will release P2, I will access P2 and I will complete my task. But B is also thinking that. So I am holding P2 and waiting for P1. So this is kind of a cycle. So A is waiting for B is waiting for A. So this is another application for topological. And another classical thing is the course scheduling. So how will you schedule your course? So suppose in your whole like in your BTech curriculum, you have five courses, and they have some depend. So course 1 needs to take before C2, course 2. Okay, course 4 needs to take before course. So same thing like this. So C1 needs to take before C2. C4 like C2. C2 is the prerequisite for C4. C4 is the prerequisite for C. And the C3 is the prerequisite for C. Now the question is that how will you like take like what will be your sequence of taking the course to cover all the course. So this is also kind of topological. So because so this is a directed graph. So if you do the topological sort, you will get the sequence. So these are the things. So basically, main thing is that cycle detection, and if there is no cycle, tell me the sequence. That is the thing. That is the whole story. Yeah. So I think that's all. I can also talk about like strongly connected component, but I think it's too late. So I think we can wrap up. So if you have any question, you can ask. Else we'll wrap up.
Sir, please share these slides, sir, in MS Teams.
Which slides? I don't have any slide.
Sir, these means these
Okay,
files
so
you
this
have sent. Yes, sir.
Okay.
This file.
Yeah.
Thank you, sir.
Welcome. Yeah.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome.
Thank you, sir.
Thank you, sir.
Welcome.